In this video, we'll be discussing about the mapping functions of the cache memory and main memory. In the previous class, we have discussed about the cache memory importance. There are number of blocks in the main memory, and the cache memory may have also number of blocks. Here it says the main memory is divided into number of fixed size blocks, and the cache memory is also divided into number of fixed size blocks. The block size of the main memory is equal to the block size of the cache memory. However, number of blocks in the main memory may not be equal to the number of blocks in the cache memory. So try to understand, if I have main memory of 4 GB, cache memory may be of 2 MB, I have block size of 16 words in one block. In cache memory also it will be 16 words per block. So number of blocks may be more in main memory, number of blocks may be less in cache memory, but the block size is same. As the block size is same, so I can take one block from main memory, keep it somewhere in the cache, and one block from the cache memory can be taken and it can be kept somewhere in the main memory. Now the question is that how the processor will know that which block of the main memory is kept where in the cache memory. So there must be a mapping function. So there are three different mapping functions are being used. One is called direct mapping. Second one is called the associative mapping or fully associative mapping. And the third one is called the set associative mapping. This can be understood. We can go for an example and then we'll see that how this mapping function actually works. Let us take an example, a cache consisting of 128 blocks of 16 words each. That means the cache has 128 number of blocks. Every block contains 16 words. So what is the size of the cache now? 128 blocks, 16 words each. 128 is 2 to the power 7. Each block has 2 to the power 4. So 2 to the power 7 into 2 to the power 4 is 2 to the power 11. 2 to the power 11 is nothing but 2048 words or 2k words. 2 to the power 11, 2 to the power 2 to the power 1, k is 2 to the power 10. So 2 to the power 11 words. So size of the cache memory is 2 to the power 11. And it is also given that main memory is addressable by 16-bit address. If the main memory is having 16-bit address, then how many memory locations can be possible? Is 2 to the power 16. If you have 1 bit, then we have 0 and 1. So 2 to the power 1 is 2 locations. If I have 2 bits, then I can have 0, 0, 0, 1, 1, 0, 1, 1. 4 locations. 2 to the power 2 is 4 locations. If I would have 3 bits, then 2 to the power 3, 8 locations. If I have 4 bits, 2 to the power 4, 16 locations. So similarly, if I have 16 bits, then I have 2 to the power 16 locations, addresses. So what is the size of that? Says the size of our main memory. The size of our main memory is over here how many? 2 to the power 16. So 2 to the power 16 is how much? 2 to the power 16 is 64k words. 2 to the power 16 is 2 to the power 4 into 2 to the power 10. 2 to the power 4 is 2 to the power 6 into 2 to the power 10. So 2 to the power 6 is 64. 2 to the power 10 is k, kilobyte. So 2 to the power 6 kilobyte of words. Main memory is of 64 kilobyte. And what is the size of cache memory? 2 to the power k. So we have given only this one, cache memory 128 blocks of 16 words. We have computed the size of the cache. It is given that main memory is 16-bit addressable. So we have computed what is the number of words in the main memory, what is the size of the main memory. So how many blocks will be there in the main memory? As you know that the size of the block in cache memory is equal to the size of the block in main memory. So what is the size of block in cache memory? It's the 16 words. So in main memory blocks also has 16 words. So how many blocks will be there? Total 64k words. Each block has 16 words. So 64k divided by 16. So 2 to the power 16 divided by 2 to the power 4 gives you 2 to the power 12. So 2 to the power 12 is nothing but 4K blocks. So 64K is the total size of the main memory. 64K is 2 to the power 16. Each block has 16 words, 2 to the power 4. So 2 to the power 16 divided by 2 to the power 4 gives you 2 to the power 12, which is nothing but 12 is 4096. So we have, if we start from 0, it is up to 4095. We have 128 blocks in the cache memory. So it is block 0 to block 127. Every block has how many words? 16 words. So here it is 16 words. Here in the main memory also it is 16 words. Now we'll see how the processor will know that which block of the main memory is mapped into which block of the cache memory by using the direct mapping technique. The direct mapping technique says the block J of the main memory maps into J modulo 128 of the cache. This J modulo 128 is nothing but the number of blocks in the cache. So it says 0 is mapped to 0, 1 is mapped to 1, 2 is mapped to 2, 127 will also map to 127. Then 128 mapped to 0 because when J modulo 128, so 128 modulo 128 is 0, so it will map to 0, 129 to 1, 130 to 2, like that 255 to 127, 256 to 0. In that way it is being mapped. That means if the processor is searching for block 128, it will definitely search in the block 0. If it is searching for block 257, definitely it will search for in the block 1, because it will put the same formula J modulo number of blocks in the cache memory to get the location in the cache memory itself. But here one problem is that one block of the cache may be mapped into multiple blocks of the main memory. That means block 0, block 128, block 256, block 512, 1024 are mapped to block 0. Block 1 is mapped to block 1. Block 1 is of the cache memory is mapped to block 1 of the main memory, block 128, block 256, 513, like that. So if I have to store block 0, I will store over here. But if 128 is requested, then I have to take out block 0 and store 128, even if the other blocks are vacant. So more than one memory block is mapped into the same position in the cache. This may lead to contention of the cache blocks even if the cache is not full, even if there are many vacant places. As these blocks are mapped into a particular block, so we cannot keep it in other locations. So resolve the contention by allowing new block to replace the old block, leading to a trivial replacement algorithm. So if it is being requested, same block is requested, then I have to go for the replacement. Now in direct mapping, the address generated by the processor has 3 parts. So what is the number of bits? Over here the main memory is addressable by 16 bits. So 16 bit that is addressable over here by the processor has 3 parts. One is called tag bit, another is called the block bit, and third one is called the word bit. The word bit specifies the number of words in a block. So can you find out how many words are there in a block? There are 16 words in a block. So if there are 16 words, 2 to the power 4 is 16, we require only 4 bits. So in the word field of the address generated by the processor has 4 bits. This block bit specifies the number of blocks in the cache memory. So there are how many blocks in the cache memory over here in this example? 128 blocks. So 128 blocks is 2 to the power 7 is 128. We require 7 bits. So 7 bit is for the block. The total is 16 bit. This is 4 and 7. So 11 bit. Rest 5 bit is for the tag bit. The tag bit is the number of blocks in the main memory divided by the number of blocks in the cache memory. How many blocks are there in the main memory? Is 4096 is 2 to the power 12. 2 to the power 12 divided by 2 to the power 7 is 2 to the power 5. So we require 5 bits over here. So this 16-bit address generated by the processor has now 3 parts: tag, block, and word. And tag field has 5 bits, block field has 7 bits, and word field has 4 bits. Now this is the direct mapping. So what is the problem over here in the direct mapping is the contention problem. So to resolve this, there is another kind of mapping that is used called the associative mapping. So here in the associative mapping, we give importance to the space. That means we want the space management to be efficient. Here it says any block of the main memory can be mapped into any block of the cache memory. So I will bring block 1, keep it somewhere, and bring 255, wherever it is backend, we'll put it over there. See, this is very easy, and this is efficient in terms of space, because none of the space in the cache memory will be vacant. So it will go on, we can go on placing the blocks in the cache memory till it becomes full. But what is the problem over here? The problem is why searching, because we do not know which block, the block from the main memory, where it is being kept in the cache. Now, the address generated by the processor has only 2 fields. One is word field, another is tag field. So word field is the number of words in a block. The same, the 16 words in a block, therefore it is 4 bits. The rest all bits are used as the tag bits, because there are 2 to the power 12 number of blocks in the main memory. Processor generates a 16-bit address. This 12 bit, to search inside the block, we require only these 4 bits. The rest of the 12 bits will be used for comparing with each of the cache when it is present. So main memory block can be placed into any cache position. The memory address is divided into 2 fields. This is word field, and this is tag field. This is flexible and use cache space efficiently. Replacement algorithms can be used to replace an existing block in the cache when the cache is full. But what is the problem? Problem is in the searching. So what we have done over here, in the direct mapping, we have 3 fields: tag, block, and word. In associative mapping, this tag, and there is no block field, only tag field, and there is a word. You will see in these 2 mapping, the searching is faster in direct mapping. However, space management is poor. In associative mapping, there is a good space management. However, the searching is difficult. So by combining these 2 mapping technique, another mapping technique comes into effect, is called the set associative mapping. So what we'll do over here, we'll make a set of blocks. We'll keep, see over here, we have a number of blocks. A fixed number of blocks will make a set. For example, if I'll take 2 blocks of the cache memory and we'll set one set. 2 blocks of cache, another 2 blocks of cache is another set. Like that we'll do. So if I make 2 blocks as one set, we say it is a 2-way set associative mapping. If you take 4 blocks as one set, we'll say 4-way set associative mapping. Now what you have, to the block 0, which block was mapped in direct mapping? To the block 0, you have 0, 128, 256, 512, 1024, like that. To the block 1, which blocks are mapped from the main memory? Is block 1, block 129, 257, like that. Now what you will do, block 0 and 1 is one set. So any block which are mapped to 0 or 1, like 0, 1 of this one, 64, 65 of this one, 128 and 129. This 120, earlier 128 was mapped to 0. 129 was only mapped to 1. Now what we will have, 128 and 129 is mapped to 0 or 1. So we have some flexibility over here. So block 0 of the cache was earlier mapped to some of the blocks of the main memory. Block 1 of the cache was mapped to some of the blocks of the main memory. Now what we have done, block 011 is made as a set. We make them as a set so that all those blocks which are mapped into 011 can be mapped into either 0 or 1. Similarly, all those blocks of the main memory which are mapped to block 2 and 3 of the cache can be placed in any of these blocks. So we said a two-way set associative mapping. So here the processor generates an address that is of 16 bits. The word field, now it has also 3 fields, that is called the tag, block and word. Instead of block, now it is called set also. Now what is the number of bits in the word? The same, we have 16 words in a block, so this bit is same, 4 bits. Now how many bits are there in the word field? The word field will have, now earlier it was how many blocks? 128 blocks. So direct mapping it was 7. But now how many sets are there? 2 blocks, 1 set. So 2 to the power 7 divided by 2 to the power 1 is 6. So this set bit will be set to 6. So set bit will be set to 6 over here. So we'll correct it from block to set and this bit from 7 to 6. So as this is 6 and this is 4, 6 plus 4 is 10 bits. So rest 6 bits will be used as the tag bits. So this has to be changed from 5 to 6. So we have in 6, now we have computed the number of bits in each of the field. Can you tell me if we have 4 blocks, 1 set, and we said it's a 4-way set associative mapping. In 4-way set associative mapping, how many bits will be there in each of these fields? The number of words in a block is same. This will be 4. How many bits are there in the set? If it is 4-way set associative, 2 to the power 7 divided by 2 to the power 2, because 4 blocks 1 set. 2 to the power 7 divided by 2 to the power 2 is 2 to the power 7 divided by 2 to the power 2 to the power 5. So set field will have 5 bits. As this is 5 and this is 4, 5 plus 4 is 9 bits. So 7 bit will be used as the tag bit. So this we say as the set associative mapping. So if you have understood, please go through these 2 problems and try to solve of your own. This is the similar kind of thing that we have discussed. The main memory is 32-bit, cache memory has 512 blocks, 32 words is. So find out the size of the main memory, cache memory, number of blocks in main memory, and then compute this. And similarly, you would go for the second one. And this is the assignment for you.